One of the new features in Dyalog version 20 is inline tracing. And this is the ability to trace into expressions function by function rather than line by line. And this is something that can be particularly helpful when dealing with tacit expressions, for example. Another cool thing with inline tracing is that you can trace directly into an expression typed into the session itself. Now, there are quite a few new capabilities to the inline tracer, and my aim in this video is to demonstrate the basics rather than trying to be exhaustive. If you're interested in learning more about inline tracing, I do recommend that you check out the documentation. See the description in the video for the details of that. But let's get into it. Let's try some inline tracing. So let's have an expression. Let's calculate the average of a numeric vector. Plus, reduce, divides, tally, 10, for example. Yeah. Now, there are a couple of ways that we can get into inline tracing from here. And one is the action menu, which has a trace inline item, or we can do the same using the context menu, and then we have the action and trace inline there via the right click. But the most convenient way is probably to use the new keystroke IT, which is by default bound to Control-Alt-Enter on Windows. If I press Control-Alt-Enter, we should open the inline tracer. We can see here that there's a couple of new things here. It says inline tracing there. There's a new symbol, 3 dots and an arrow ahead, which is, if you hover over it, trace inline. So the same keystroke, Alt-Control-Enter. And we have this red box that highlights the next function that is about to be executed. And over here, if we make it a bit bigger, we have the right argument pane. So what this tells us is that the next thing that's going to happen is that the iota will be executed with a right argument of 10. So if I press the Control-Alt-Enter again, we can now see that the box has moved to the left and has grown, and it is now showing the whole of the tacit expression. And if we look to the right, in the right argument box, we can see now that the right argument that will be passed to the tacit expression is the result of the iota 10 evaluation. But this is actually where it gets interesting. I can now step into this tacit expression. And this is a fork, and we have 3 functions. We have the sum reduce as the left tine, we have the tally as the right tine, and the middle tine is the division function. So if I step into this now, we can see that the first function to be executed in this fork is the right tine. So tally with the right argument of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next function is the left tine, the sum reduce, also with the same right argument. But now the middle tine is a dyadic function, the division, and when we get to that, we can see that we also get the left argument box opening. And what we have now is the division about to be executed with 55 to the left and 10 to the right. So 55 divides 10, which should give us the 5.5 as we execute that. So that is quite a neat little tool to see, especially with tacit expressions where it might not be immediately clear the order of execution. Let's try something a little bit more involved. So let's have a function called GTA for greater than average. So greater than average is going to be a function that from a numeric vector, it's going to select the numbers that are greater than the average of the vector. There are several ways we can do this. I'm going to write it a little bit longer than I would have to, just because I want to be able to highlight some features of the inline tracer. So nums gets the right argument, and then I'm going to append a 0 to the end of it. And the reason why I do that is that we want to protect ourselves against an empty vector. So if we get past an empty vector, we don't want to get a domain error or something when we try to divide by 0. So I'm going to stick a 0 on the end. And then I'm going to calculate the average like we did before. The average gets the plus reduce divides tally of the nums, and then we're going to do compress, so that we're going to calculate the location. We're going to calculate a binary mask of where the numbers are greater than the average, and then we're going to use that to compress. And we can do this, for example, like so. Compress commute, because we want to avoid a set of brackets. The average filtered by filtering the numbers, like so. Is that correct? Yes, hopefully. Okay, let's save that, see if it works. GTA IO to 10. That looks plausible. But let's get into this now with inline tracing. So I'm going to trace into this. So the interesting thing is my own function now, right? So I'm going to trace into the GTA. So now we can see here. Actually, what I'm going to do is I'm going to open the left argument box here a little bit so we can see some more stuff. So now we're about to execute the gets here, and we can see here to the left we have a green box now, and that's symbolizing that what we have here is a variable. Yeah, so we have name nums, and it currently has no value because we are obviously creating a new local variable here in this defun. So let's step through that. And here then we can see here we also have a left argument that is a name, but this time it does have a value. Actually, let's make it a little bit bigger still. We can see now we can actually, in this modified assignment here, like we can actually step into this. Yeah, we can step in one more in this. We can see that the append there, the concatenate will add a 0 to the end of the vector. Here we have then the next function to be, which is the expression for average, which we did previously. We can just go through that in a couple of steps, and then we have obviously creating a new variable again. And here then what we do, the first thing that we do is create this binary mask. Yeah, so we have a less than. We have a 5 on one side, which is the average, but we added the 0, and then the numbers to the right. So if we create that, we can now see that we have a function, the compress commute function, takes the vector to the left and the mask to the right. But if we actually step into that, we can see the effect of the commute. If we step into that, we can see there that the effect that it had was basically to obviously, like commute does, it swaps the order. But this is something that we can actually now see very clearly the effect. We skip that again, and then we get the numbers out. And this helps again understanding a complex expression. So if you have, for example, a tacit expression again, or something that has lots of commutes in there, you can see the effect of what the commute does by just stepping through one step at a time. You should see the argument changing place. Now, there are a lot of things that you can do here, like I mentioned earlier. Like if we do go back into this, well, one thing, for example, here you can do, like in the layout, you can choose where you want the debugger window to open. The classic mode here, you have everything detached, and then you can choose to have the debugger on the left as well if that's what you want. But if we go into this again, you can see here that the menus changes, and what we've been using here is the left argument and the right argument aspect panes, which is so this, we can see the right argument here, and if I kind of reopen the left argument again, you can see that. But there are many more of those that you can use. That probably in the most use cases you're not going to be needing, but they are there if you really do need them. So if you have something that's very complicated, you can have more windows here that you can drag around. that shows the previous function, the previous right argument, and you can even have, if you're using bracket axis, for example, there you can see which axis you are currently investigating. So I think for most cases you're probably going to be fine with just using the left and right arguments. But if you do need sort of more insight into this expression, those aspect panes are there for your use. So that is inline tracing. It's a new and powerful feature, and I think it's going to become very useful to be able to step through tacit expressions and other things that where you really need the detailed walkthrough of an expression. So try it out.